Thanks, guys. All right, so raise your hand if you've ever watched a film because a friend told you they liked it. Great, okay, cool. And on a greater scale, we take recommendations in our daily lives from systems, not friends, without even thinking about it. So from what films you should watch to which items you should purchase, many of today's most engaging and commercially important applications are providing personalised experiences to users and are able to make personalised recommendations quickly and efficiently. So if we think about Netflix and Hulu, they both use your previous watching behaviour to make suggestions to you. And similarly, a system like Spotify might suggest what you should listen to next, based on what you've already listened to. So clearly, recommendation is big business right now. In this talk, we're going to look at a particular class of recommendation engines known as collaborative filtering. We'll start by thinking about the case where the user has made a specific rating on an item, such as, I give this film 5 out of 10. And we're going to use the industry standard algorithm known as alternating least squares to get recommendations in this case. So a quick Google search will tell you that Spark's MLlib library has an implementation of ALS in it, but perhaps you don't know what it does, how it works, and how to get the best out of it. So we'll focus on that today. Right, raise your hand if you've already been to a talk about recommendation engines this week. Okay. Hopefully I can teach you something new today and cement what you already know, and I think my net new topic today is going to be talking about implicit data. So, for example, the data could be purchased items. Just because you bought an item doesn't mean that you liked it, or even that you bought it for yourself. So how are we going to make recommendations in that case? The example we'll be working with is some music data. So we've got a data set that shows the number of times that users have listened to a particular artist. And for that music data, we're going to see how to build a recommendation engine using Spark's built-in tools. We'll then go on to see how we can put this into production by splitting a system into microservices. So let's get started with collaborative filtering. What we've got ourselves here is 11 people. The simple idea behind collaborative filtering is to cash in on the similarities between users. We're going to use those similarities to make predictions. So if we look at one specific group from that set of people and look at the way in which they rate products, we can see that they're fairly similar, and we can imagine how to make predictions when there's missing data. So here we see that everybody gave product A 5 stars, everyone gave product B 3 stars. Can someone give me a suggestion for what we might predict user 3 might give to product C? 4, perfect. Something in the region of 4 stars. So that method's all well and good when we've only got a small number of people. We can make sensible suggestions. But what happens when the data size grows? So what we really have is a matrix that looks something like this, where M and N are large. We've got loads of products, and we've got loads of users. If we think about Netflix, for example, in June this year, they had 118 million paying users and nearly 15,000 films and programs. And that's not accounting for the number of user profiles within each paying account. So first off, we can see that that grouping method is no longer going to cut it. Another thing we have to deal with is that this matrix is very sparse. So a particular user has rated a negligible proportion of the films that are available to them. So we want to use what we know about them and what we know about similar users to those to make predictions for how they're going to rate the product. One thing I'm going to point out here is that everything we are talking about today is very general. So if you have any data that you can fit into a matrix like this of the form users and products, then you're going to be able to use this method. We could build on it using metadata and tags and so on, but we're not going to cover that here. So let's have a look at alternating least squares. The idea is to factorize a ratings matrix R into 2 factor matrices U and P which when multiplied back together are going to give us an approximation of the original ratings matrix, but the gaps will be filled in. So the empty places in the matrix, denoting where a user has not rated the product, will now be replaced with an estimate of that rating. So U is our matrix of user factors, and the kth row of U relates to user K. Similarly, P is our matrix of product factors, and the jth row of P relates to product J. Why is this useful? Well, if we want to predict how user K might rate product J, we just multiply those two vectors together. Great. So why is it called alternating least squares? Well, it's alternating because the process that generates those matrices U and P is done first by fixing U, optimizing for P, and then fixing P and optimizing for U. And we repeat that process. It alternates. The least squares bit comes from that optimization. When I say we're optimizing to minimize least squares error on those recorded values that we already had in the matrix, the ones that were filled in before we started this process. So if we go back to our bigger matrix, the estimates are now filled in, and from here you can see that it's straightforward to give predictions to users. You could return, for example, the top predicted films for yourself very simply with this data. So that's all well and good when the data is of the form of ratings, and we call this explicit alternating least squares. But what if our data isn't of the form of ratings? Let's think more about that. So suppose this is me, and I have listened to a song once. What does that mean? Does it mean that I liked it? Does it mean that I disliked it? We don't know. I might not have even been listening. It might have been playing on my laptop with my headphones plugged in whilst I went to make a cup of tea. Similarly, what can we infer if I haven't listened to a song? It might mean that I dislike the artist, and I know I dislike them, so I don't bother to listen. It might just mean that I don't know this song exists, or it might be that there's another 15 million songs in the world I could be listening to and I haven't discovered this one yet. So we can't be 100% sure, but that missing data might tell us something. And I think you would agree that if I've listened to a song 100 times, it was probably by Taylor Swift, and it probably means that I liked it strongly. I'd want our model to be much more confident in saying that I liked the item than I liked the first song A that I'd only listened to once. So we want to capture this in a model. We want to be able to take that implicit data and use it to make predictions to users. So if you're interested in learning more about this technique and the model that we're going to use, grab a photo of this slide right now. The methodology we're going to use is taken directly from this paper, and the paper is really nice. It's not maths heavy, it's nicely readable. So yeah, check it out. I can put that slide up at the end if anyone missed it. All right. So when the data is implicit, the aim of the model is to be able to say, will the user like this item? This is captured in a number between 0 and 1, with 1 denoting yes, they will like it, and a 0 denoting no preference. Now that does not mean that they dislike it, it means that they do not like it. So to put this another way, the opposite of saying the user is likely to like this is not the user is likely to dislike this. So this model isn't going to be able to tell us what we think users won't like. The preference for a user is captured in this P here, and it's got 2 subscripts. So we've got U for the user and I for the item. So for every user and every song, we can imagine having a preference. Okay, the next component of the model to introduce is R, which is the recording. In the music example, the recording is just how many times I listen to a song. Again, it's specific to a user and an item, and you can think of other examples of recordings. For example, how many times you purchased something in a supermarket. Or it might simply be a did you purchase it, did you not? How many hours did you watch a TV program for? And so on. We've got a relationship between the preference and the recording, and that's captured as follows. So we say, if the recorded value is greater than 0, the preference is 1, otherwise it's 0. Now, in the music case, that boils down to saying that if you listen to a song once, you positively like that song, otherwise no preference. But I just spent some time arguing that if you've only listened to a song once, we don't know if we like it, right? So how are we going to capture that? Well, that's captured through this notion of confidence. We want to have some confidence in small recordings and more confidence in larger recordings. Similarly, we want to have some confidence in recorded values being 0. So if the recorded value is 0, according to our model, the preference is 0, and we have some confidence in that. We're saying if the recorded value is 0, we don't know, we don't think they like it, so the preference is 0. And in order to capture that, that's the 1 up front. That's the contribution we get when the recording is 0. Alpha is a tuning parameter, and it measures how much of a difference we weight the confidence between a recording of 0 and a recording of 1. Later, we'll look at some of the other parameters of the model and talk about alpha a bit more and see how the parameters affect the output. So when we put this model together and implement alternating least squares, the equation that we're now minimizing is this one here. So we're trying to find the user vector u and the item vector x such that this quantity is minimized. Okay, so we are at Spark and AI Summit, and so far I've talked about AI, but I haven't mentioned Spark, so let's go. All of the code I'm going to show you is written in Python, but obviously you can use your favorite Spark compatible language without any major difficulties. So what does Spark offer to us? Well, in Python, there's this PySpark MLlib recommendation module, and within that, there's an ALS class, and that meets all of our ALS needs. So let's see how we build a model in Spark, and then we'll go on to make some predictions. In order to build a model, we're going to need some data. The data we're using is the last.fm data set. So it's an open source data set, so you could go and download it and have a go yourself. There's 17 million recordings in there from 360,000 users and 200,000 artists. And that's what the schema of the data looks like. So we have a user ID, an artist ID, the artist name, and the number of times that that user has listened to that artist. Within the ALS class, there's this train implicit function, and it takes in a few arguments. So it takes in the data set in the form of an RDD. And again, as I mentioned earlier, any data that we can write in this form, user ID, product ID, recording, or user ID, product ID, rating, we can use this function for. We've also got some tuning parameters there. So in our case here, the recording is the number of times that the user has listened to that artist. Just in terms of building a model, if we build a model on that data set with 17 million rows in it, on my laptop, it takes about 2 minutes. In practice, we've been doing standard training and validation on the model. So we split the data into a training set and validation set. We evaluate on the validation set. We look at the mean squared error, or your favorite loss function. And then we change the parameter values, and we repeat this process to compare our models. So let's talk about the parameters. Rank is the width of the matrices U and P, or the number of features in the feature vectors. So here on the right, we can see the impact on the mean squared error as we change rank. So clearly there's something going on there, so you should definitely make sure you're doing some tuning. Lambda is a parameter which prevents overfitting of the model. Most models have one and certainly should have one. When I introduced the minimization term earlier, I said it looked like this, but there's actually an extra term which prevents overfitting. And so the lambda is this lambda out front there. And again, we can see the impact of lambda on mean squared error. So the alpha parameter turns up in the equation for confidence, and it relates to the scale of the recordings. It can be used to enforce a strong relationship, a strong increase in confidence between no recording and one recording. So suppose the recording is related to the number of times you downloaded a song rather than just listened. It's still implicit data, since we don't have a rating, but if you downloaded a song, you'd be much strongly in belief that you enjoyed it compared to if you didn't download the song. So in that case, we'd set alpha to a large number. That paper that I showed you earlier suggested that alpha equals 40 works well in most cases, but I would suggest tuning. Finally, iterations. So iterations is how many times we oscillate between that process that generates the matrices U and P. Now, iterations, unlike rank and lambda, isn't quite so straightforward to tune for. The root mean squared error is monotonically non-increasing in iterations. So this means that as we increase the number of iterations, our model is never going to get worse. But it's unrealistic to say, let's set iterations to 1,000, because that's going to take ages to run. So in practice, we've been using the simple rule of thumb that if the incremental reduction in mean squared error at iteration t compared to iteration t minus 1 is less than 1,000th, we stop. Right, so now we've talked about building the model and training the parameters, but we need to be able to make some predictions. Again, that ALS class has got us covered. So there's this predict all function that takes in an RDD of user item pairs, and it returns a prediction under that model that you trained. So let's have a little look at this anecdotally. Here I'm just looking at songs that have been listened to by user 1. Artists, sorry, not songs. Now, I'm getting old, so I've heard of some of the older bands like Bon Iver and Passion Pit, but I don't know much about the later ones like Led Zeppelin. But I think it's fair to say that this user has quite an eclectic taste. And anecdotally, if we make some predictions for them, we see the output here: Red Hot Chili Peppers, Coldplay, PJ Harvey. Fairly eclectic. Okay, so far we've seen how to do alternating least squares on pen and paper. We've talked about the equations. We've seen how to implement it locally in PySpark, and that was all done in a Jupyter notebook. That'll be made available on my GitHub, so if you want to go and have a look and play around, then go for it. But how do we turn this abstract algorithm into something useful on a larger scale? We need to find ways to implement this algorithm within an application and make predictions to users at that large scale. Think back to Netflix. We can't just exactly build a system in a notebook to serve 118 million customers. So we're going to build a system which runs in the cloud, and every component runs in a container. Microservice architectures are a popular way to build applications by structuring them as a collection of cooperating lightweight services that don't hold any state and communicate by well-defined interfaces. This means we can deploy them easily in the cloud. There's many good things about microservices, and I'm going to ignore most of those today, except for one, and that is the ease with which you can swap out components. So the model we talked about is basic. It just needs data. But where are you going to store your data? Do you want to put it in Cassandra, Kafka, Postgres? Well, you can put it in your favorite database, and you can even change where it's stored. Microservice architecture is allowing us to do that. In a similar vein, in production, we might want to see how different tuning parameters or post-processing options perform. And microservices allow us to run multiple models in parallel and conduct control experiments and compare the output. The other thing we could look at is how business metrics are impacted. So I've only talked about minimizing mean squared error of the model. We have an example that I'll show you in a moment where we do some movie predictions. And we found that the model that minimized mean squared error was giving some very peculiar predictions. And that was because there's a small number of films that have maybe only been watched by one person, but they rated it very highly. So if your user factor vector is deemed similar to that person's user factor vector, it's going to predict to you this really weird film that they liked. You might like it, but we'd rather return something that we had more confidence in. And so to do that, what we ended up doing was filtering out from predictions any films that had been seen by fewer than, say, 50 people. And that made a huge improvement in the results that we were getting in terms of what you would see and what you could actually go and watch. But in terms of mean squared error, it made the model marginally worse. So a fully functional example of a recommendation system working with Apache Spark is available from radanalytics.io. Radanalytics.io is a community project, and it's focused on empowering development of intelligent applications with such contemporary architectures on OpenShift. Now, if you're not familiar with OpenShift, it's an enterprise-grade distribution of Kubernetes, and it has a great developer experience. But your main takeaway from this slide should be that this is all open source, so please go download it, build a recommendation engine, switch in your own data, play around, and get in touch with us. So on this site here, we go through the tutorial to build your own movies recommendation system, but it will work with any other data set, so go for it. Okay, so it seems that I talked quite fast, but I am Sophie Watson. You can find me on Twitter and GitHub at SophWatts, and there is my email address. Yeah, happy to take any questions.
If you have a question, raise your hand. I'll bring you the mic.
Hiya. You mentioned that you could potentially include metadata and tags into this type of model. How would you go about that?
So within this architecture, I feel that it could be easily added as an extra microservice. So I would have a post-processing microservice that would probably sit nicely with the predictor. So when you're making predictions to people, you could then incorporate that tags data. The modeler, you could do something more complicated with the modeler, but the beauty of ALS is its simplicity and its ease. So I would definitely add that in a post-processing microservice. And I guess that post-processing microservice would just need access to the predictions that are made and the data store. So if you stored your tags with your data. So it should be quite lightweight and easy to implement something. In Amazon, for example, there's that common case where you order an iron. And so you've looked at irons, you buy an iron, and then you bought an iron, but it continues to recommend irons to you because it thinks you really love irons and you want multiple. So things like that would be able to be filtered out in post-processing, but you could still use ALS as is out of the box.
I just wanted to clarify my understanding of the model. The matrices that you're that they have the same, presumably they're of the same size as your underlying data set that you're trying to, apart from the kind of column reduction. So does this mean that you end up with quite a lot of parameters in the model? So sort of deploying it to, I guess, small devices would be impractical. You're always going to need to be evaluating a model from a sort of server environment. Is that correct?
the factor matrices U and P together are much, much smaller than your original ratings matrix R. So there's a row for every user. So if you have 14 million users, you've still got 14 million rows. But the width of those, which is determined by rank, might be, for example, 5. We found 5 work quite well on the movie data set. And so similarly, P it might be 20,000 products and 5 wide. And that's significantly smaller than your ratings matrix R, which was 20,000 by 15,000.
Any more questions?
Hi, thank you for a great talk. Very interesting. You mentioned that you did some filtering on the films that only a few people had watched.
That's right.
And you noticed that that gave you better real-world results,
Yeah.
but affected the error rate. How did you measure the real-world results? How did you know it was better?
Good question. I mean, very anecdotally, I made predictions for myself. So I put in a load of Disney films that I adored and rated some horror films terribly. And the things that came out were, I got some German horror films predicted to me as you will love this. Yeah, some action movies, and I showed no interest in action movies at all. So it's very much on an anecdotal basis, and I appreciate that that is very hard to incorporate into a system in practice if you're working in production, you know. You set it off, you don't want to have to check everybody's predictions before they go. I imagine if you were really going to run this in production, you would want to, every so often, have, you know, once a week or something, have a human checking that the output is looking okay. But again, it's not a great solution at scale.
Thank you.
That was an awesome talk, thank you. So I'm interested why you chose a model-based approach for your recommendations as opposed to a neighbor-based approach, for example.
As opposed to what? Sorry?
As opposed to a neighbor-based approach.
Oh, a neighbor-based. We didn't put much thought into it. So when you talk about a neighbor-based approach, do you mean sort of finding someone similar to you? Okay, so I think underlying alternating least squares, it is doing that. If you compare the factors, so the rows of the matrix for specific users, you can find that they become very similar for users who are similar. So it is still collaborative filtering and using that neighbours data, but I'm happy to chat about it more offline if you want.
More questions?
Hello, first of all, thanks for the talk. Did you try approaches like LightFM and especially, let's say, integrating embeddings of titles, of descriptions of the film, and then based on that, new nearest neighbor search using FICE or Spark, other nearest neighbor approximations?
We absolutely have not looked at that at all,
Okay.
but if you do it, let us know how it goes.
Okay. It's a little bit better, but still.
Okay, okay.
This will be the last one.
Okay, yeah. So I was wondering about the score, like of when you have a rating of 0, like not the rating, but how many times a person has listened to this song or whatever, and what you conceptually explained about what it actually means, and that on the end, like in the end, you had to remove the the songs or the movies that nobody actually had listened to. So I was wondering, how does the confidence score takes into account this, that a song that I have not heard could be a song that I'm interested to, but a song that nobody has heard of probably is one I'm not interested in.
So that the model itself, we have not changed. So we pass all of our information into the model. So you're right, if there's a song in the database that only 1 or 2 people have listened to, it's still going to be in the model. We are not changing the equation for confidence based on the items. There are some examples of that in the paper. So given that few people have actually listened to a song, you could incorporate that in the confidence. And that's certainly something that they hint to in the paper, but I don't know whether anyone's done it, but it would be interesting to see. But yeah, we're just shoving all the data into the model and then post-processing it out. Perhaps not the best way, but who knows?
Okay, unfortunately, that's all the time we have. Let's all thank Sophie.